Well, so in this class we are going to discuss the estimation of fugacity coefficient for real gases. Now, here again I would like to mention we are first going to discuss the estimation of fugacity or fugacity coefficient, whatever it is, for real gases, and then we are going to do it for the condensed phase. It's the same for the liquid as well as the solid. After that we go for discussing the fugacity coefficient for one particular component in a mixture of gases. Now, whenever we do, we start from the same two equations. For a real gas, this is this. For an ideal gas, the equation is this, because every time my standard for all particular systems that I use, my standard is going to be an ideal gas. Now, I subtract one from the other. So, on subtraction, what do I get? I get d of mu minus mu 0 equals to each and every term. I subtract these two terms, I subtract these two terms, I subtract these two terms, right. So, therefore, this gives us R T d ln f by p, which is nothing but equal to phi, and this is equals to V minus R T by p dp. Then I can integrate each one of them. What should be my integration? I should be integrating it from a condition where I know the fugacity, or in other words, I should be integrated it from the ideal gas state, which is applicable at p equals to 0. Again, I recall that all gases or all substances exhibit ideal gas behavior at high temperature, low pressure. Since the temperature is constant here, the only way to approach the ideal gas state is by starting from a very low pressure. So, therefore, at that particular low pressure, say it is p equals to 0 to p equals to p. At p equals to 0, fugacity equals to pressure. So, therefore, this is equals to 1 to f by p, and here mu minus mu 0, this should be equal to 1 here, and then it should have a value of mu minus mu 0 here. So, on integration, what do I get? I get mu minus mu 0, sorry, it is not 1, it is 0 here, because mu equals to mu 0 here. Mu minus mu 0, this is equals to R T ln f by p, which is equal to integral 0 to p V minus R T by p dp. This is the standard equation which I have also mentioned here. This is the standard equation which I use in order to find the fugacity of the gases. Now, the first thing which appears is this can also be written down as V dp minus 0 to p R T d ln p. Integrating this is not difficult. For integrating this, we have to use the PVT behavior of gas. We have PVT behavior or the equations of states relating the P, V and T of real gases. We have already discussed those equations, and as we have found out, there are several types of equations: the cubic equations of state, the virial equations of state, etc., etc. We can use any of those equations. The only thing that we need to remember in this particular case is the same thing which had happened when we were trying to derive the departure functions for entropy and enthalpy, that all these equations, they are in terms of pressure explicit form. For example, P equals to something, whereas in this particular case we would like to express V in terms of P. So, therefore, in order to perform that, again I would like to remind you what do we need to do for that particular case. You have already done it. For those particular case, we can write it down. V dp is nothing but equal to dpv minus p dv. So, therefore, when we write down R T ln f by p, then instead of V dp, we can write it down as dpv minus p dv minus R T d ln p integral 0 to p. This should be equal to V 0 to V, and here for p equals to 0, it is R T, this is going to be P V, right. So, therefore, for such particular conditions, we find that ln f by p will be equal to P V by R T minus 1 minus 1 by R T integral V 0 to V P dV. whereas we know P v by R t is equals to Z. So, therefore, this is Z minus 1 by R t V 0 to V P d V. So, therefore, in this particular form if we use, then in that case we can use any particular equation, the cubic equations of state, and in this particular slide what I have done is I have mentioned the different cubic equations of state which we have already discussed, and using these cubic equations of states I have also written down the final forms of the fugacity, coefficient in terms of Z, the two constants A and B, where usually the constant B it refers to the correction due to the non-negligible volume of the molecules as compared to the volume of the gas, and A arises due to the interaction between the different molecules. Well, here there is one particular thing which I had forgotten to mention in the last class, which I would just like to mention here. When we are dealing with the standard states, we say that it is the at very low pressure, then in that case you must remember that under the standard state conditions we neglect the interaction between the molecules, and therefore, for all the gases the standard states are different due to the structure and the molecular nature of the different gases, and not the way that the gases interact. Well, so therefore, this is the first way of determining the fugacity coefficient of the gases, that is by the PVT behavior. Now, apart from the PVT behavior, this particular approach is similar to the way we had defined the ways of estimating the departure functions from entropy and enthalpy. We should also be in a position to determine fugacity or fugacity coefficient from compressibility factor as well, isn't it? From the compressibility factor also we should be able to define it. For that, in what way should we be expressing this particular equation? We can express it as d ln f by p, this is equal to V minus R t by p dp. This is the same thing which I had written, which is nothing but equals to Z minus 1 by p dp. Now, here if I integrate it from 0 to p, in this particular case we are going to integrate it from f by p equals to 1 to f by p, and this equation also we can define it from 0 to p. Now, in this case we need to remember that Z becomes equal to 1 for the limiting conditions. So, therefore, in this particular case we can write ln f by p is nothing but equal to integral 0 to p Z minus 1 by p dp, right. And we can also write this down as Z minus 1 by pr dpr integral 0 to pr. Can we not write it down in this particular form? And then I have also displayed to you the different compressibility factor charts which gives Z as a function of pr with tr as parameter. We have already discussed those particular charts. So, therefore, using those particular compressibility factor charts we can find out Z, we can substitute Z here, and we can find out the value of fugacity coefficient. If you observe this equation very closely, there is another interesting thing that you find. We find that when we are writing this equation in the form of integral 0 to pr Z minus 1 by pr dpr, if you observe, we find that from this particular equation phi it is a function of Z pr, or in other words, what do I mean? And we know Z is a function of tr pr. So, from here does it suggest that just like entropy and enthalpy departure functions, phi also obeys the two parameter law of corresponding states, or in other words, we should be able to generate curves like phi versus pr with tr as parameter, and from these particular curves, in absence of any other data, we should be able to find out phi from these particular charts. Let us see whether this is such charts. They are available for different types of fluids. They are available in several thermodynamics books, and we find that this particular chart, it is applicable. Both of these charts, they are there for different values of PR, for lower values and for higher values of PR. And it is also important to note that from this particular equation we can also use a 3-parameter law of corresponding states for greater accuracy, where we can define the 3-parameter law in terms of the acentric factor proposed by Pitzer. We can write it in this particular form or in the log base 10 form, which gives the equation as which gives this particular equation. And once we know this particular equations, then, or rather once we know how phi 0 and phi 1 varies with TR and PR, we should be in a position to find out phi. So, therefore, these graphs, they show us the variation of phi 0 with TR PR, and also the next graphs they show us the variation of phi 1 with TRPR. So, using these curves also we should be in a position to find out the fugacity coefficient from this generalized compressibility factor charts. What is the next technique by which we can find it out? We should also be in a position to find it out from residual volumes. We should be in a position to find it out from residual volumes, and this is very evident if we look at this particular, what is this particular expression? This is nothing but the volume of a gas minus the volume of the same gas, 1 mole of the same gas, provided it was behaving ideally under the same conditions of temperature and pressure. So, this particular term, it is nothing but equal to delta V star, right. So, if we have data on delta V star, then we can directly write ln f by p is nothing but equals to 1 by RT 0 to p delta V star by RT dP. But for this, what do we need to know? We need to know how delta V star by RT varies with P. So, therefore, we need to suppose it varies in some particular vague way, and we would like to find out the fugacity at some particular pressure P. Then the area of the curve starting from P equals to 0 to P equals to P, this whole area under the curve, that gives us an idea about the fugacity. Now, here I would also like to mention one particular thing. See, we can use whatever you have said, we can use the PV behavior, we can use the compressibility factor chart, but it is not sufficient to know the PV behavior or the compressibility factor value at the pressure, at the particular pressure of interest where we want to calculate the fugacity. Why? Because if you observe all the equations, you find for each of the equations the integration starts from 0 to P. So, therefore, if I have to integrate over this entire range, either this equation or this equation, we need to know how volume varies with pressure, how compressibility factor varies with pressure, right from 0 pressure to the pressure of interest. So, it is not just sufficient to know the behavior of the gases at the pressure of interest in order to calculate fugacity. We need to know the behavior of the gases throughout the entire range from the very low pressure, almost 0 pressure, to the pressure of interest. This is one thing which makes the calculation slightly difficult, and therefore, depending on the availability of the data, we have been suggesting the variety of methods which we have proposed. Now, all these methods that we have discussed, they are based primarily on PVT behavior of gases. Suppose we do not have an idea regarding the PVT behavior, then how should we find out the fugacity coefficient? Again, we can find out the fugacity coefficient remembering that dg, or rather g, equals to h minus Ts, mu equals to h minus Ts. So, therefore, at constant temperature d mu equals to dh minus T ds, What is this equal to? This is R T d ln F. So, therefore, we can also find it out from thermal data as well, right. And for this particular case also, again the only problem is the identification of the standard states. We start from here to here. Accordingly, H has to be evaluated from very low pressure, under which the gas behaves ideally. So, therefore, this is equal to Cp0 dt dH minus T S0 to S ds, which gives us H minus H0 minus T S minus S0. So, from which we can write it down as R T ln F by F0. If F0 equals to P, then this can reduce to R T ln phi, provided F0 is equals to P, and this is nothing but equal to delta H star minus T delta S star. So, therefore, and there is one more thing which I would also like to mention, that usually what we do is, the other thing what we do is, we usually use the Redlich-Kwong two parameter equation of state. So, in the next class we will be first discussing how to estimate the fugacity. We have discussed how to estimate the fugacity of gases, definitely pure gases, but real gases, single component real gases. But if you are dealing with phase equilibrium problems, then definitely the most common problems are liquid vapor equilibrium or solid vapor equilibrium. So, therefore, if we have to find out the equilibrium, we need to have an idea about the fugacity of the gas as well as the fugacity of the condensed phase under any particular condition of temperature and pressure. Regarding fugacity of gases, we had a good amount of discussion. Next class, we are going to discuss the fugacity of the condensed phase, and then we would like to take up the two parameter Redlich-Kwong equation of state, which is very frequently used for gases as well as for the condensed phase. And we are just going to, this is particularly important, or it's particularly frequently used for in the hydrocarbon industry. So, we are going to end with our discussions on how to use the equation, the Redlich-Kwong equation of state. Thank you very much.